So today we're going to talk about atomic spectroscopy. So a good question to ask is, what is atomic spectroscopy? If you haven't used our AA, you will before the semester is over. And the way our instrument works is a liquid sample gets aspirated into a burner where the flame is hot enough to break the molecules into individual atoms. So atomization is the term we use to describe the process of breaking something into gaseous atoms. There are two types of atomic spectroscopy. You can look at absorption or at emission. So for absorption spectroscopy, which is how we usually run our instrument, there's a lamp that's used to pass electromagnetic radiation of the correct frequency through the flame where those atoms are. And the intensity of the transmitted radiation is measured, and that is proportional to the concentration of the analyte. In atomic emission spectroscopy, we're looking at the radiation that's emitted by the hot atoms. So the heat from the flame is exciting them, and then their electrons, when they come back down to a lower state, they emit radiation, and that's what we're measuring. So for emission spectroscopy, there is no lamp required. So this sort of gives an overview of the two different modes. For absorption spectroscopy, we've got some sort of a light source passing through the flame. The analyte is going to then absorb some of that light and go from ground state to excited states. We look at the amount of light that comes through. We use a monochromator to filter that down to a smaller band of wavelengths, and then we've got a detector. In emission spectroscopy, the atom in the flame is excited by the heat of the flame, and as those atoms relax, they emit electromagnetic radiation, and we are just looking at the radiation that comes out of the flame. Again, we need a monochromator and a detector. So the two instruments, well, actually, one instrument can be used to do both, and they're very similar. Any questions yet? Yes?
What's a monochromator?
A monochromator is a device used to filter out all but a select wavelength. Any other questions?
We run the absorption, right?
Yeah, we usually run it in absorption mode. That's the only way I've ever used that instrument. But it can be done as an emission. Any other questions? So the monochromator selects the wavelength that will reach the detector, because we don't want the detector to just see all the light from everywhere coming through. So we've got for absorption, we've got our lamp that's providing light. Our sample is coming up through the burner and going into the flame, where it's turned into atoms. The light comes through the flame, and we're going to look at how much light gets through. The monochromator selects the wavelength. It goes to the detector. The signal there is very small, and so it needs to be amplified and then ultimately goes to the computer. The precision with this is 2%, which is not bad. It's very sensitive, and there's a limited range in which you can use, because you can't overwhelm the flame. If you absorb too much of the light, you won't get a linear response curve. So if your solution is too concentrated, you may need to dilute it. And I know in Chem 1A we did, some of us do an experiment using milk. And you digest the milk, and then we analyze the calcium. Well, there's way too much calcium in the milk, and so we have to dilute it by a factor of 100 to use it on the instrument. So there are different ways of heating or exciting the analyte. Our instrument has what's known as a pre-mix burner, in which we have the sample, the oxidant, and the fuel all pre-mixed before it goes into the flame. So it looks something like this. There's different configurations, but they all work approximately the same. So we have a tube from our sample, and it's not very high tech. It's just a little thin tubing that you stick in a beaker or whatever you have your sample in. The oxidant, in our case just air, is blowing through here, and it blowing through sucks sample up into the nebulizer. We also have fuel coming in here. As the sample gets pulled through the nebulizer, it hits a glass bead, and it breaks into a fine mist of droplets. It's called a nebulizer because it nebulizes the solution, nebulization, formation of small droplets. Then there's some baffles, and what these baffles do is they disrupt the flow of the gases, so they cause more mixing to happen, and they also serve to block large droplets. So we want the small droplets to get through. We don't want any large droplets remaining to get through. So any larger droplets, when they hit these baffles, will just run down to the bottom, and then they'll go out the drain. So then we have our spray chamber, and in here we've got our mixture of fuel, oxidant, and analyte, and it goes up into the flame. Only about 5% of the original sample actually makes it to the flame. Any questions? What's important for our purposes is not that we understand theory behind it, but just the general idea of how the instrument works.
Okay. I was gonna ask, like, the fuel doesn't, and the oxidant doesn't mix with their analyte?
It does.
Oh.
Yeah. So the sample becomes a fine mist, and it mixes with the air. Our fuel is acetylene. It all mixes in that chamber and comes up here where it burns. Yeah, so it's all mixed together. Any other questions? Yeah.
Is there a reason why acetylene is used?
Yeah, there are different combinations of fuel and oxidant that are used. Some of it has to do with what's more convenient. Air is very convenient to use because it's just all over the place, right? Sometimes you need to use oxygen, and so that, is a little more hazardous. Acetylene is very flammable. Obviously, you need something flammable, or you won't have a flame, right? But different mixtures will burn at different temperatures and have different properties. So in the flame, the solvent will evaporate. The samples I've run on the AA have all been aqueous, and so there's a bit of water in there, and that will vaporize in the flame. The sample will vaporize and decompose into atoms. Mostly what we analyze on the AA are metal atoms, and metal atoms can cause a problem because as they rise through the flame, they can form oxides and hydroxides. And those are going to have different absorption spectrum than the metal atom itself. And so that will reduce the sensitivity, it'll lower the signal. So that can be overcome by messing around with the flame. So if we have what's called a rich flame, that has a lot of fuel in it, as opposed to the oxidant. And so the excess of carbon species will help to reduce the oxides and the hydroxides back to the metallic atoms, and that will improve the sensitivity. If you have a lean flame, it has extra oxidant, so excess air or oxygen or whatever you're using, and that will get you a hotter flame. So different flame conditions are optimal for different elements, but that's one of the things that can be altered to make the analysis work. So the most common fuel-oxidant combination is acetylene and air, and that'll give you temperatures of about 2400 to 2700 Kelvin. So that's nice and hot. Any questions? Another type of atomic absorption uses a graphite furnace instead of a flame. And so there's a drawing of one of these here. It's made out of graphite. Graphite, of course, is combustible. And so this graphite furnace is not held at a high temperature continuously. You put the sample in, you heat the furnace very quickly, you get your signal, and it cools back down. So this is doing a cooling, heating cycle. So there's a sample port in the top, and that's where the sample is introduced. Inside, there's this curved platform. Here's the end view, and you can see the curved platform here. The graphite furnace is electrically heated. So you run electric current through the graphite, and that causes it to get very hot. In order for us to get a good signal, we don't want our sample to be directly onto the wall of the furnace. We want it here in the middle. This is going to use a lot less sample because instead of needing to put your sample tube in a beaker and have it drawing up liquid, here you're just going to inject some through the sample port, and you can use as little as 1 microliter of sample. It has high sensitivity because we are not diluting the sample, and the sample is going to remain in the optical path longer than in a flame. So the optical path is through the length of it here, and so you've got your sample there being vaporized, and you'll have it there for several seconds. The precision isn't as good here. It's only 5 to 10% with a manual injection, but if you use an automatic injector, you can get better precision. Because here, how much you put in there is going to affect your signal. Any questions? So there are 3 heating steps. Over here on the right, we have a graph showing temperature as a function of time. The first step is a fairly low temperature, drying the sample just to remove the solvent. Then we have a step where the temperature is ramped up, and the idea is to char any organic matter that might be in your sample. It's also called pyrolysis. That step can generate smoke. We're taking optical measurements through this furnace, so obviously we don't want a lot of smoke. We'd like to get the smoke out of there before we actually atomize our sample. These 3 graphs here all correspond with each other, so you can see that we're taking, up here we're about at a minute, and we're going to actually get to atomizing our sample at about 80 seconds. So we char the sample, and then the temperature in the furnace shoots up very rapidly, atomizing our sample, and that's when we can read the signal through that furnace. That's called atomization. And there you're going to get temperatures up to about 2550 Kelvin. That can only be held at a high temperature like that very briefly. In the one reference I looked at, it said 7 seconds. Because if you keep it up there, your furnace will begin to burn up. So these furnaces do not last forever. Yeah. So there are some potential problems with the furnace, and some of those can be alleviated by using a matrix modifier. So the matrix is all the other stuff in your sample besides the analyte, right? Sometimes when you're charring your matrix, your analyte might evaporate or it might burn, and so that's not going to be good. So a matrix modifier might slow evaporation of the analyte so that the matrix can char away, or it may increase the evaporation of the matrix so that the analyte gets left behind. It's also possible to do pre-concentration by injecting and then evaporating multiple aliquots before the charring and atomization steps. So you can inject a sample, heat it so it will dry, inject another sample, heat it so it dries. You could do that several times if you're trying to get a very low detection limit. In this graph here in B, we're seeing that there's some absorbance occurring here during the charring step. That could be due to smoke, or it could be due to something in the matrix that's absorbing at our chosen wavelength. And then when it's atomized, we get this nice steep signal here. I honestly don't know what graph C is. Don't know. Another type of instrument uses inductively coupled plasma. So plasma is that mysterious fourth state of matter we don't talk about in general chem. Here, instead of using a flame or a furnace, we're using a plasma, and the plasma is going to get much higher temperatures, 6,000 to 10,000 Kelvin. So this is just crazy hot. As you can imagine, an ICP instrument is going to be more expensive to purchase. It'll also be more expensive to operate. So the plasma gets energized by a radio frequency induction coil that's wrapped around a quartz torch. So here's the quartz torch, and we've got this coil wrapped around. So we're going to feed our sample, aerosolized, and is that a word, aerosolized? Made into an aerosol in argon gas, is going to feed through this torch, and then the plasma will be lit with a spark from a Tesla coil that ionizes the argon. Free electrons then are accelerated, and they heat the gas by colliding with atoms. It was kind of a strange process, but you get this really, really hot plasma. And this shows you there's differences in temperature as you go from right down here inside the coil up to above. And so the temperature that you are looking at will vary depending on how high above the coil. So you can use a pneumatic nebulizer similar to the one I described for the flame spectroscopy instrument, but you can actually increase your detection limit. You can lower it by an order of magnitude by using an ultrasonic nebulizer. I'm not going to go into the details of this, but it's kind of cool. It uses an oscillating piezoelectric crystal here to vaporize the sample, and then it goes through a series of heated tubes and cooled tubes and a membrane desolvator. And when it comes out the end, we've removed all of the solvent, and we have very small solid particles of the sample. So that can get a better detection limit. Another way to improve the detection limit is to view emission along the length of the plasma instead of across. And that can happen with the flame as well. If you look down the length of the flame, you're going to get more signal than if you look across the flame at a right angle. Any questions? We don't have one of these, but they exist. Detection limits. So there's detection limits, and then there's the region where you can get accurate quantitative analysis. So to get a good quantitative analysis, you need a concentration that's from 10 to 100 times the detection limit. The detection limit's going to vary by the type of instrument, and it's also going to vary for the different elements. And so this is a table which is really not very interesting unless you're trying to do something in particular. I just happened to notice potassium and calcium here, and we've got a little key down here. So the first number is the inductively coupled plasma emission, then flame atomic absorption, graphite furnace, and then inductively coupled plasma mass spec, and we'll talk about that at the end. But here for the potassium, the graphite furnace is much more sensitive than the inductively coupled plasma. For calcium, they are much more similar. but you're going to get a lot of variation in detection limits for the different elements. Over here it shows that some of these require dinitrogen monoxide, acetylene flame, and that's difficult, so it's better to use a plasma for those. And the blue color indicates ones that are best analyzed by emission. It's a table showing some detection limits. This is looking at a nickel-1 ion at a wavelength of 231 nanometers. And it's just showing the different detection limits for different instruments. We've got the inductively coupled plasma, atomic emission with the pneumatic nebulizer, 3 to 50 nanograms per milliliter. You change to an ultrasonic nebulizer, and you drop the detection limit a factor of 10. Graphite furnace can go even lower because of that possibility of pre-concentrating your sample. And then the mass spec version is, of course, the most sensitive, also the most expensive. Isn't that how it goes? So temperature can affect the strength of your signal. It does this in a couple of ways. It can alter the degree to which the sample breaks down into atoms. If your sample's not breaking down completely, then you're not going to get as good of a signal. It also can affect the fraction of atoms that are in the ground state, excited states, and even ionic states. So in atomic emission spectroscopy, the stability of the flame temperature is very important because the emission spectroscopy depends on looking at the atoms that are in the excited state emitting energy. And the fraction of atoms in the excited state is relatively low. So a small change in temperature can cause a significant change in the fraction that are in this excited state, and then that can affect your signal. In atomic absorption spectroscopy, temperature control is not as important because most of your atoms are in the ground state, and a little bit of temperature change is not going to affect that. What you're looking at is atoms in the ground state absorbing energy, electromagnetic radiation from the lamp, and so the temperature control doesn't matter so much. ICP, inductively coupled plasma, is almost always used for emission rather than absorption because the temperatures are so high that you have a significant fraction of your atoms in the excited state, and then you don't need a lamp to provide the light. So in terms of instrumentation, one issue that has to be considered is what's called line width. So we're looking at a relationship between absorbance and concentration that comes from Beer's law. And so in order for the absorbance to be proportional to the analyte concentration, we need the line width of radiation that we're measuring to be substantially narrower than the line width of the absorbing atoms. And this is something that I was looking at 3 different textbooks, and they just really don't explain this very well. So this is my best interpretation of what they're saying. So if this is the intensity of the signal as a function of the wavelength, if you are measuring something that is on the edge of this steep curve, then a small fluctuation in the wavelength that you're monitoring is going to cause a big change in the signal, right? So what we want is we want to be measuring a very narrow portion in the middle of a larger region so that we don't have to worry about getting close to the edges. We get a much more stable signal that way, and that allows the absorbance to be proportional to the concentration. The monochromator selects the bandwidth that we're looking at, but it is limited. These absorption lines are extremely narrow. They're much narrower than a monochromator filter can supply. So the monochromator bandwidth is about 100 times greater than the atomic lines. So then it becomes important that our light signal has a very narrow bandwidth or line width. There are two mechanisms that broaden atomic spectra, and the books aren't clear on this, but I actually think these two things help us out, because my understanding is that these are broadening the line width of the absorbing atoms. We've got the Doppler effect and pressure broadening. So the Doppler effect happens because the atoms in the gas state are moving. And if they are moving towards the light source or moving away from the light source, they're going to see different wavelengths or different frequencies of light. This is the same effect that, when we hear the trains go by, the pitch of the sound changes after it passes, right? It's getting higher and then it drops, because the sound is traveling towards us and it's all compressed, and then as it's moving away, it gets stretched out. And so the
Wavelength and frequency?
Yeah,
So the wavelength, the longer frequency?
Yeah, so the longer wavelength, as it's moving away, you've got a longer wavelength, and as it's coming towards you, you've got a shorter wavelength. And so the sound, the pitch goes up and down. So that happens, because we've got these atoms moving, and so we're going to get different frequencies from them. That causes broadening. Then we also have pressure broadening from collisions between the atoms. So we've got colliding atoms. The higher the pressure, the more collisions there are. And atoms that are colliding with each other will absorb a broader range of frequencies than atoms that are not colliding. So that can cause broadening. So this is showing in the black the width of the absorption line, and in the blue here the width of the lamp emission. And that's for a hollow-cathode lamp that we'll talk about. Any questions? So the hollow-cathode lamp, you need to use one where the cathode is made out of the metal that you're analyzing. So in our AA instrument, we have several different lamps. You have to have a lamp that matches what you're going to analyze. So you can really only analyze a single element at a time. What we're doing here is we're using the element to generate the frequencies of light that it will absorb in the flame. And so it's really kind of genius, because we're getting exactly the right frequencies, and they're going to be very narrow. So in this hollow-cathode lamp, it's sealed and it's filled with neon or argon gas at a low pressure, because we don't want any pressure broadening in here. So we have our hollow cathode. If we're analyzing calcium, this would be made out of calcium. There's an insulating disc here and an anode. We've got a quartz or glass window, depending on what frequencies of light we're looking at. We don't want the material of the lamp to be absorbing the light. So we apply a high voltage between the anode and the cathode. That ionizes the gas that's present in there, neon, argon, one of the noble gases generally. The gas gets ionized. Cations will accelerate towards the cathode, where they're going to knock atoms from the cathode into the gas phase. So we're going to ionize, say, our argon gas, and then it's going to make cations, which are going to be attracted to the cathode. And so they're going to fly in here and smash into it. It's called sputtering. And so it's just going to knock little bits off. Those gaseous metal atoms then are excited by collisions with high energy electrons, and they're going to emit photons as they return to the ground state. So they are going to emit light at the same frequency as the calcium in the flame is going to absorb.
So then that light goes through the quartz or the window?
Yeah, so the light will go through the quartz window and then through the flame. Yep. Any questions? So as with many instruments, we need to worry about the background signal. This is showing, I believe this was, well, I don't remember what it was, and actually it doesn't matter. This is actually a very narrow range of wavelengths from 247.5 to 249.5 nanometers, and we're seeing several narrow bands of emission here, well, absorbance. But all of this is riding on top of a background signal that's about 0.3 absorbance units. When you get up around nine or so absorbance units, things get kind of wonky because you're absorbing too much of the light, and so you're not going to get a good linear signal anymore. So we need background correction to distinguish our analyte signal from the background signal. That background signal can come from many different sources. We can get absorption, emission, and or optical scattering that can cause that background. And all of that, any one of those, can come from either the sample matrix or from the heat source itself. So the flame, the plasma, or the furnace can give us emission, it can absorb, we can get optical scattering of the light, and all of that will introduce this noise, this background signal. Any questions? So if you've used our instrument, you know that you have to go through this process of zeroing it beforehand, and it makes all these chunking sounds and clunking sounds, and you're like, is it okay? That's fine, it always does that. So auto zero is going to correct for the basic background absorption that's always present. Our instrument uses a deuterium lamp. The deuterium lamp gives a very broad emission, a wide range of wavelengths. And so we take the hollow-cathode, which has the very fine lines that we need for analyzing our sample, and we've got the very broad emission from the deuterium lamp. And what the instrument does is it alternates between the two light sources. So the hollow-cathode lamp light is absorbed by the analyte. It is also absorbed by the background. So that's what this is saying here. So the light from the hollow-cathode is absorbed by the analyte and the background. The light from the D2 lamp, the deuterium lamp, is really only absorbed by the background because what is absorbed by the analyte is so small relative to what's absorbed by the background that it just really doesn't matter. So essentially it's unchanged by the analyte signal. So by looking at the difference between the signals you get for these two different lamps, you can get your analyte signal. So this graph is showing absorbance as a function of wavelength. This is the wavelength that we're measuring at. So the background is this curve here. If you have running a blank, usually we use DI water. You run the blank, and it's going to go through and look at the wavelengths and see what that blank is giving you. And then it can subtract that. The problem is, what if you have something in your sample that's not in your blank that also absorbs where your signal does? And that can cause a problem. So this is just auto-zeroing. We're setting this as 0. And then when we put our sample in, we measure this, and we're looking at the difference. And we get a nice signal. What's more problematic is when you have something like this, where this is your blank, but here's your sample. And so there's something else in here that's absorbing, right? And it's not uniform. And so if we're measuring against this, which is where our auto zero got set, we're going to be overestimating our sample, right? So another way that you can compensate for this background is the instrument can look at absorbance at nearby wavelengths and essentially, it's like in chromatography, it's essentially drawing a line here, connecting these two parts of the curve, and then determining, okay, in the middle here, we're going to call that 0. All of that's done in the instrument, so we don't have to worry about it too much. Any questions?
Is it just like taking the difference between the area of the two curves?
I don't think it's taking the difference between the area. I think what it does is it will look at, it'll change the wavelength to each side and see where it drops precipitously. And then it'll say, okay, well, this is no longer the sample and that's no longer the sample. And so we're going to call that the background. The exact details of all that are kind of hairy. And thankfully, we don't need to understand them. Any other questions? One of the cool things you can do with the inductively coupled plasma atomic emission is that you can actually measure multiple elements at the same time. And so this is a photograph of such an instrument. Here you've got your plasma, and the light is coming in from the plasma because your sample's going in there, and it's getting excited, and it's emitting light. So we direct the light from the plasma into the instrument. The light is going to run through a shutter, and then it's going to use a prism and a grating. And what that's going to do is it's going to separate the light vertically and horizontally. So it's going to spread it out into a two-dimensional grid based on its wavelengths. And so the light bounces around, it comes over here and hits the detector. It's a CID detector, stands for charge injection device. I didn't know that. Learned something new today. That detector is much like the sensor in a digital camera. So you've got different pixels, and each pixel is going to be receiving a different wavelength from all of these different wavelengths that are spread out. And so the computer monitors each of the pixels. Each pixel then is going to correspond to a different element. So you can actually measure up to 70 elements simultaneously. So that's pretty cool. Any questions? Of course, there's different types of interference that can occur. Spectral interference happens when your analyte signal overlaps with other signals. Those signals could come from a species in your matrix. It could come from emission of your flame or your furnace. So interference from the flame, we can get rid of that through background correction. If you've got overlap of signals from other elements in your sample, the simplest thing is to choose another wavelength. Elements absorb light at more than one given wavelength, and so the chances are good that if you just choose a different wavelength that it absorbs at, that will not overlap with the same problematic element. We can get chemical interference. This is caused by anything that's going to hinder the atomization of the analyte. So there are various releasing agents that can be added. One of the things, if I remember correctly, is phosphate ion. Phosphates are not soluble, and the phosphate will bind onto your metal atom and prevent it from being atomized. So there are releasing agents that can compete with those problematic species. A fuel-rich flame or a higher temperature in your flame can also help depending on the nature of the chemical interference. Ionization interference is a problem for the alkali metals. They ionize very easily, and so the heat that's atomizing them can also cause them to become ions. Well, ions have different energy levels than atoms, and so they're not going to absorb in the same place, and so you're going to lose signal. So depending on the ion that's giving you problems, you can add an ion suppressor, an element that will decrease the ionization and increase your signal that way. Any questions? So one way around a lot of types of interference is by using the method of standard additions to make your standard curve. Have you guys talked about that a little bit? So this is showing an example of looking at strontium in water, in aquarium water and in pure water. So here's our standard curve in pure water. We're trying to measure the strontium in some aquarium water. The standard addition method, you take your sample and you measure the absorbance, and then you add known quantities of strontium to that sample. And so in this way, your standard curve has the same stuff in it that your sample does. So if you have interfering ions, they're going to interfere with everything, and it's probably going to be more linear. When you do it this way, you get your line here, and then you extrapolate the line, and where it intersects with y equals 0, that is your concentration of your unknown. So this intercept over here is telling us that the concentration of strontium in the water was 7.41 parts per million. And so that's a good way to get rid of some interference. There's also inductively coupled plasma mass spectrometry, which in a way, is this even atomic spectroscopy? It's like, well, I don't know, right? Maybe it's just mass spectrometry. But this is one of the most sensitive techniques. It's really great for trace analysis. So you form analyte ions in the plasma, and then you direct them into a mass spectrometer, which is going to separate the ions based on their mass to charge ratio. You can get linear ranges over 8 orders of magnitude, which is huge. And you can get a detection limit that's 100 to 1,000 times lower than that furnace atomic absorption. So very low. Of course, that comes at a cost, though, because this is going to be a lot more expensive than our simple little instrument. So this is an interesting summary of these different methods. So we're looking at the flame absorption, furnace absorption, plasma emission, and then the plasma mass spec, looking at the different detection limits, and we see that the plasma mass spec is by far the lowest detection limit. Linear range, plasma mass spec wins again. Precision is measured in the short term and in the long term. Instruments tend to drift, right? Looking at possibilities of spectrochemical interference. Now, we do get mass interference with the plasma. So, plasma mass spec. So, if you have 2 ions that have the same charge and the same mass, then you can get a lot of problems, because it's called, what is it called? I forgot what it's called. There's a name for it. But there's a lot of really kind of crazy ions that can form, like argon plus and other odd things that don't happen at room temperature. But in the extreme heat of the plasma, they can happen. And then you've got different isotopes as well. And so you combine isotopes and ions, and you can get some mixing up, right? So that's a problem. Sample throughput, giving you the amount of time for each element. And that's, of course, going to vary. Dissolved solid, sample volume, and purchase cost. Purchase cost, not sure what those numbers mean, right? maybe just if we're comparing it relative to the flame absorption, this is maybe 10 to 15 times as much. That would be my guess for interpreting that number. Any questions? That's all.